and we're going to basically look at what it is, why it's important, how heat load interplays with that, how reset relates to turn down, because quite often they're used, the terms are used interchangeably, even though they're not really. And so we'll discuss the difference. And then finally, we'll look at system efficiency as it relates to reset and turn down. So that's tonight's agenda. And without further ado, we'll jump into it. So turn down is basically the ratio between the highest fire setting and the lowest fire setting, or in total, the operational range of a particular boiler, or in a cascade system, a number of boilers. The ratio varies by boiler, by company, by manufacturer, by model. So if a boiler has 3-to-1 turn down, it means that at its lowest fire setting, it will be operating at 33% of full capacity. If it has a 10-to-1 turn down, it means it's operating at, it can operate at 10% of its full capacity. And there's reasons why. Turn down is additive. So as you add more boilers to a system, the maximum output increases, but the minimum does not. So if you have 2 boilers with a 10-to-1 turn down, your total system turn down is 20-to-1. And 3 obviously would make it 30-to-1. Essentially, the more boilers we put in a cascaded system, the higher the turn down ratio. Now, you get to a point where that really doesn't matter anymore, but certainly turn down does help you match the load much more effectively than 1-to-1. And so here's just an illustration. If we had a couple of LXs in this case that have an 8-to-1 turn down, and we cascaded the pair of them, we now have a system with a 16-to-1 turn down. So why is it important? Because very few systems need to run at their highest output all the time. If you've designed for quote unquote load design temperature, you're only going to be there a very, very small part of the time, typically about 1% of the heating season. So you have to have enough capacity to meet that demand when it's there, but really most of the time it's not. So it doesn't make sense to run the boiler 24/7 at its full output. And the ability to turn it down gives you a much better load match.
Well, you know what? Let's think about what you just said there, Teddy. So it's not good to run the boilers constantly 24/7. And that is a great point to bring up, because if these guys understand turn down and multiple systems, you don't want to run a boiler at its maximum firing rate at 100% of its life expectancy. You want to run each boiler at a certain percentage so that each boiler sees a certain amount of runtime, so you're getting the same wear on all the components. Same wear on the igniters, same wear on the sensors, because remember, if you got a unit going 100% all the time and the other one doesn't come on, if you get them all going on a certain level, like 60%, next one goes on at 70, just keep rising. You're gonna see a lot of usage.
Let's just to be clear on what you're saying, that's in a cascaded system.
Right.
We're going to look to distribute runtime over a number of boilers in the system. With a single boiler, the turn down, what it does do is prolong the life of all the components, because you're not cycling as frequently. If you can load match, you have longer run times and longer off times, which increase comfort. You don't have temperature fluctuations as much. And if you don't, every mechanical component ever made at some point in its creation was designed around something called, oh my God, now I'm having a senior moment, but it's duty cycles. So you may have something that's designed to have 100,000 duty cycles. You may have something that's designed to have 1,000,000 duty cycles. Different components have a different duty cycle built into it. But the fact of the matter is, the more often you cycle it on and off, the quicker you get to its duty cycle life.
I just bring that up because it's real important cycling that. And the other thing is turn down can also be a hindrance too on small systems. So, all right, Uncle Teddy, we're good on questions, I think, so we can keep rolling.
No questions yet? Okay.
No, pretty good.
Excuse me. So without a good turn down ratio, you don't have a whole lot of options for how much fuel is used. If you have a high turn down ratio, it can be more efficient because it'll operate at a lower capacity during low demand times, but you'll also have the ability to meet peak demands when it's required. And again, I think that the urge in this industry, it's funny, I'm sure you've all heard of Dan Holohan. It's something he said many years ago in a seminar. I never forgot it. He said the urge to oversize in the hydronic or really in the heating industry in general is stronger than the sex drive. I have heard, I don't know how many people tell me over the years, they do a heat loss. Now, mind you, heat loss already has fudge built into it, but they do a heat loss. They say, oh, let's say we need 80,000 BTUs, and then they stick in something that has 120 output because they don't want the callback. Well, they're not doing their customer a favor, honestly. If you, well, but let's get into this further, but it's not doing anybody a favor. So better load matching through turn down also serves, as I said, this goes back to the duty cycle thing I was talking about. It minimizes the on-off cycling, which reduces temperature fluctuation and the negative effect of short cycle or mechanical equipment.
Ted, I think you're frozen and I keep freezing too. I think it's this hotel we're in. Just want to interrupt there. If anybody's wondering why we're freezing, we're in Utica, New York at a hotel. And Ted, you froze and I froze for a couple minutes there. So.
Uh-oh. So I'm not sure what people heard or not, because once I'm doing the...
Oh, I can hear you fine. Just your picture froze. I wanted to let you know.
Oh, well, it's just a picture,
It was your good side.
Nobody cares what I look like anyway, so it really doesn't matter.
It was your good side. You know what I mean?
So heat load. Let's talk about heat load now, right? And there's fluctuation. Obviously, heat load calculation is the whole point of it is to match the right amount of installed heat capacity for a given outdoor design temperature. And the heat load itself refers to the amount of heat that's required to keep the building at the desired temperature. So they're one's related to the other, but they're not exactly the same. So in North America, that's expressed in BTUs per hour and at a given design temperature. And here's how that works for those, honestly, these days, pretty much everybody does a computer, aided heat loss if they're doing one at all. And God, I hope you all are doing it one way or another.
Yes, please.
But so you understand the math behind it. It's really not difficult. It's that universal heat formula where Q is the load in BTUs per square foot. U is a transmission coefficient, which is U value is simply the inverse of R. So if you know the R value, it's just 1 divided by the R value is how you get to U value. A is the area that you're looking to calculate the heat loss through, whether it's a wall, a window, a door, a roof. And honestly, to do a building, you have to look at it component by component, because every one of these, the wall, the windows, the roofs, the doors, everyone's got a different R value, and consequently a different U value. And delta T is the temperature differential between what you want to be maintaining the indoors and what you're designing for outdoor. So that looks like this here. If we were looking at the heat loss through this wall, this 8x10 wall, and we did the calculations at an R value of 28, that wall would lose 115 BTUs per hour at that particular temperature differential. So that's with maintaining 70 in the building and an outdoor temperature of 30. So heat always moves from warm to cold. Doesn't matter up, down, sideways. I know there's this fallacy that heat rises. That's not the case. Warm air rises because it's more buoyant, but heat simply moves from warm to cold.
That's why do they tell you where to put your baseboard? Right by the windows.
Well, that's where, yeah, because that's where it's going to feel the coldest.
It's gonna feel the cold.
Like, so design temperature varies by location, and there are all kinds of ways. There's ASHRAE, there's Manual J, there's a book put out by the Los Alamos Lab. There's Energy Star. They all, ASHRAE, they all print or publish design temperatures for various locations. And that's quite often expressed as the 99 percentile. So what we're designing for is not the absolute coldest that it ever gets at a given location, but rather as we average over a long period of time, it's that temperature at which 99% of the time it's either at or above. So there are going to be instances, transient instances when the temperature drops below design, but the thermal sort of flywheel effect of the building is going to keep you from ever actually feeling that. And that's why oversizing just, really just doesn't make sense. In a moment, we're going to look at, let's see here what happens next here. So yeah, so here's a pretty good example. This is, I picked Syracuse, New York, but I mean, this profile can be found for any given location. The reason I picked Syracuse is because I'm going to be there over the weekend, and it just, that kind of made sense. But so we have a design temperature of 0. According to the Energy Star chart in 2019. However, the average January temperature is 24. And if you're designing for a 70-degree indoor temperature, right off the bat, your system average is going to be only 2/3 of full capacity. And if you look at the average cold temperature in that chart in January, which statistically is the coldest month, even the average cold temperature is 16 degrees. So you're still 16 degrees above what is stated as design. So at best, there you're running at what, about 80% of capacity. And
It's a nice chart.
Pardon me?
It's a nice chart.
Yeah, I thought this was really, really interesting and kind of was a good illustration of what I've always felt, that design temperature, in particular, if you're looking at a 99 percentile, by default, 99% of the heating season is going to be at or above that temperature.
Mm-hmm.
If you work that out in a number of hours, you'll find that, like, for instance, I think I worked it out where in Syracuse, over the course of a 6,600 degree day heating season, you were only at design temperature for about less than 150 hours total.
Yeah, I mean, you look at that graph, you can see it.
And so again, oversizing just you're not doing anybody any favors. It just does reducing efficiency.
Yep.
Yeah, it's an interesting chart. And then here's the other piece of that. is that even on those very, very cold days, now this looks at a sort of hourly temperature profile, again, for Syracuse, but it's going to be very similar wherever you go. In fact, actually, these might even be a little more extreme in some other places where the very cold is much more transient, because Syracuse tends to be a fairly cloudy climate. But if you look at this, you'll find that the coldest temperature on a given day is generally right around dawn, just before dawn. And you'll see how that moves, in the very cold months, and that tends to that very cold moment tends to be reflected as the day's getting longer. It becomes earlier and earlier in the morning. But that's what I was talking about, that thermal flywheel effect. Let's say you had a day when you were at, or even, a couple degrees below design temperature. Again, that's right around dawn, and that thermal flywheel effect of the building already being warm, even though the boiler, your heat plant, might not exceed the design load at that moment, the flywheel effect of the building actually keeps the occupant from ever really feeling that.
And then we add boost function.
Yeah, well, and that's another thing entirely, where we take the reset and we actually play with it to increase the output if the boiler doesn't sense a temperature rise in the return. The algorithm says if we're running and not seeing a temperature rise, the logic is that we're not putting out enough energy to increase the temperature in the building. So the boiler, if you've enabled boost, and you really should, will automatically look at that and start raising its outlet temperature to match what it feels it needs to do to warm the building. Outdoor reset plays into this actually in a very important way, because that changes proportionally. Think of that like cruise control in a car. So if you want to maintain a constant speed, let's say you want to go 70 miles an hour. And when you go uphill to keep going 70, you've got to give it a little more gas. That's analogous to increasing the temperature. And when you're going downhill and you want to maintain 70, you back off on the gas. And that in effect is like decreasing the outlet temperature. So really, cruise control is outdoor reset as applied to a heating system. And the type of distribution system then affects the characteristics of reset as well. In other words, do you have baseboards? Do you have radiators? Do you have a radiant floor? And so this is how that looks. Again, if we look at 70 being the baseline, we're designing for 70. And as the outdoor temperature falls, the outlet temperature going to the system temperature has to rise. And these are typical. Obviously, they're, each system's going to be a little different. But, let's say a fin tube baseboard is going to need to have its temperature increase much more rapidly and have a much higher target temperature than a radiant floor. And even different types of radiant behave differently. There's a slab radiant, a thin slab, a slab on grade. There's a thin slab radiant, like an overpour. There's staple up, with plates or without plates below the floor. Radiators tend to be sort of halfway in between. They're kind of a mass system, so they don't need as hot a temperature as a fin tube or a convector like an air handler. Tend to be the ones that need the hottest temperatures as the temperature falls. So this is typical. As I said, it's not each system needs to be designed as a system. So condensing boilers do offer higher efficiency, and they can definitely reduce heating bills over a conventional boiler. But, and this is the caveat, they have to be installed correctly, and the controls have to be set up so the boiler will condense as often as possible throughout the year. The other
There you
piece
go.
of this, of course,
That's
is
right.
we just looked at is that is dependent on the distribution system that's either already in the building, in which case you don't have control over it, but certainly in a new system, you have a lot of control over. Even baseboard, for instance, can be sized to run at lower temperatures. I mean, this the thought that it always needs to run at 180 is a fallacy.
Yep, that's right. That's right.
You know,
Amen.
in other words, you at 180, let's say, in the average baseboard, the residential baseboard gives you, I think, roughly 550 BTUs a foot. But at 140,
580, 580 at that temperature.
580. And the other thing I want to talk about, and it's a little bit dangerous thinking that you're always going to get 580 because
Yeah.
you get 580 out of the first foot of it. But in an 8-foot piece, you're not getting 580 out of the whole thing because every foot that you've given off some heat means the next foot is getting a little bit lower temperature.
That's why you're
And
better
so
off dropping the temperature and constantly
that's why
running that way.
when I calculated baseboard, I always calculated it for less than what they list as the per foot outlet,
Right.
because that's only, like I said, it's really only good in the first foot. Because as you progress, that temperature's dropping and you're giving off less.
Well, look at these baseboard manufacturers. They got charts that go all the way down to 110 degrees and go up to 130. That's a nice area to be.
Yeah, and
Just
there's
like
they
you said,
show
constantly
you how you derate it for lower temperatures. Now, honestly, I mean, you could put a baseboard system in that's going to condense the majority of the year. You just need a lot more baseboard.
Yeah, just got to spread that delta T out. Listen, I'm delivering 145 degrees to my cast iron rads and they rain.
Yeah, and I actually, in half my house is radiant floor and half my house is panel radiators. And
Oh, you can run them low. Oh,
what
you
I
can run.
did was I oversized the panel radiators. Again, I went through the derating chart so I could run them at the same temperature I run my radiant floor.
That's just like adding baseboard. That's the best way to go.
Yeah. So I mean, it's about system design. And if you're
That's
putting in
right.
a new system, you've got control over a lot of different variables if efficiency is important to you. But those are all discussions you need to have with your customer. In other words, simply throwing in a condensing boiler in a system that is not really designed to condense and then not activating the outdoor reset kind of defeats the purpose.
On, off, on, off, on,
Right.
off, and they call that short
And
cycling, and they call it waste energy.
you get short cycling, and quite honestly, if you don't condense, and you have to condense, you need return temperatures of you know it'll start to condense at a return temperature of 140, but really you want to get it closer to 130 if you really want effective condensing.
Well, and
And
constantly,
now
it's
that's
just
not
like
a supply temperature; that's a return temperature. But so then you're looking at what the delta T is across the system. But even that is kind of it's a tricky thing because technically, let's say we design a baseboard system, they say, well, you're designing for a 20-degree delta T, but if you actually measure the supply and return temperatures, you'll find it's pretty rare that you're really getting a 20-degree delta T.
right.
That's that design condition.
I like your analogy comparing it to cruise control. You set it in cruise control. You're sitting at 65 miles per hour because that's all I drive in a van because I'm sitting on the phone book. So you're driving down the road 65 miles an hour. You're not wasting fuel. You're constantly going. That's like when you go to a red light. Do you speed up and try to catch the next light and get through it and waste all that fuel? No, just constantly go at one pace, at one temperature, and that's a great analogy. Because if you run a system like you do a heat pump, they constantly run. Heat pumps constantly run. You don't want them to shut down because if they shut down, you start to work that compressor up. So, these are things that, like you said before, Every time the boiler goes on, it starts the igniter, it opens the gas valve, it starts the fan, it's working all the components.
Well, and that's the other thing from an efficiency point of view. Not only does the short cycling uh, uh, kind of increase the wear and tear on the equipment, but the boiler is the least efficient on its startup. That's so you achieve maximum efficiency at a steady state condition.
Well, just figure on startup, the circulator alone has to increase the amp rating to move the water through there, because now, let's say you didn't flush your freaking system out and you get sediment in there. So I'm just saying, like you said before, cruise control is the way to go.
Yeah, and steady state. So ideally, you're ideally you're utilizing both turn down and reset to maximize the efficiency of the equipment and the longevity of the equipment.
There's a great question here.
Sure, what is it?
I like this question. With the room thermostat or room sensor, will monitor the room temperature and help the boiler modulate based on room temperature stat setting. It will help that boiler. The person who asked this is Kevin Gerard. And Kevin, thank you for asking this question, because it's a great question. And let me address it for you. If you decide to go with the NTI room sensor, you will get the best of both worlds, which is exactly what Teddy's talking about, designing a system correctly. If you do it that way, you're going to get indoor and outdoor comfort. If the outdoor reset and the indoor reset are hooked up, you have features to get the best efficiency, because you will be able to increase to cover your indoor temperature and satisfy that and maintain that at an efficiency rate and maintain the outdoor temperature. Great question, Kevin.
Yeah, so the advantage of indoor feedback to further refine outdoor feedback. Outdoor reset is ideal if you have a box with no windows, because now you would negate the effect of solar gain, for instance, right? And internal gains. That's the other thing in buildings, is that outdoor reset assumes that you have a steady indoor temperature and a given outdoor temperature. And so that's kind of what you would say a gross adjustment. The fine tuning accounts for internal heat gains and the effect of solar gain as well through windows. And so a particular, um, um, the ideal system is going to utilize both. It's going to use the outdoor reset for the gross adjustment and the indoor feedback for the fine tuning. So this kind of goes to what I was talking about earlier, where condensing boilers will work best, with low return water temperatures. You want, for the best condensing, 130 or lower. And as that return temperature rises, your efficiency drops off to, let's face it, once the return temperature is over 140, you're basically running a very effective standard efficiency boiler. That's all it is. And so, it will operate in the high 80 percentages, 80 percentiles, but it's not going to be, if it's not condensing, you're not up in the 90s. So you can look at the literature all you want. It's wishful thinking that if you put a 95% efficient boiler in a system that isn't going to condense, it's never going to operate at 95% efficiency. It's as simple as that. You can't fight physics. So low temperature heat emitters like, inflow radiant, air, oversized and air handler maybe, or low temperature baseboards, panel radiators, are best suited to condensing boilers because they operate at lower water temperatures. See, and again, to go back to what we were talking about with baseboard, high temperature baseboard can definitely work in a condensing system if you use outdoor reset and you size the baseboard accordingly. But during the course of a heating season, even if you've not oversized the baseboard, in the shoulder season, you just don't need design output. So during the course of the heating season, a condensing boiler can maximize its efficiency, even with conventional baseboard. And we hear this all the time. Well, you know, I've got a baseboard, why would I use reset? Well, because there's going to be a lot of time of the year, in the spring and the fall, you need heat when it's, 45 or 50 degrees outside, but it's certainly not design temperature. So there's no reason to be giving that baseboard 180 degrees. So, when you have a mild outdoor temperature, the cooler boiler water will still heat the house, and it'll be condensing, and you'll maximize your efficiency at least in the shoulder seasons.
Looking good on the question.
Yeah, what is it? Question?
We're rolling. Nope, no questions. We're doing good, bud.
No questions. I've either lost everybody, they don't care, or maybe I'm explaining it wrong.
I'm answering. A couple questions came in. Bill McKay had one. Kevin had that question, and then I just sent his response back. So we're good.
Oh, good.
Okay. Doing great.
So, good. So this kind of just reiterates what we were talking about, the milder outdoor temperatures in the spring and fall. Again, shoulder seasons, even on a conventional high temperature system, will enable, if you're utilizing reset, now you have to utilize the reset to experience condensing temperatures. So to summarize, I think here we go. Turn down is going to attempt to match the boiler output to the load. From an efficiency point of view, a system efficiency, there's really only going to be a moderate increase from turn down only. It doesn't matter how much it turns down. If you're not decreasing temperature, if you're just reducing the output of the boiler and you don't condense, you will get modest efficiency increases. Now, it will increase comfort because you're going to reduce temperature swings and short cycling. And because you're reducing short cycling, you're going to prolong the life of all the system components. So there's a distinct advantage to turn down, but not in the sense strictly of system efficiency. To truly be efficient, you have to enable the reset, and that is getting the return water to condensing temperatures. So again, you're not going to condense above 140, and if you can get it down to 130, you're going to be fully condensing. Again, return water temperature, not the supply. So, again, that's about delta T. If the system has a 10-degree delta T and you go out at 150, you're going to come back at 140. In other words, and so for true efficiency, you got to have reset, and ideally you're utilizing both. So now you're lowering the BTU output of the boiler to match the reduced load on the building, and you're reducing the temperature of the water going to the system to increase condensing.
Teddy, we got one. Teddy, one question here I want to answer. It was from Ed. When you automatically connect the outdoor sensor, will it automatically connect right to the unit? Yes. Anytime you connect the outdoor sensor on any one of our newer boilers, it will automatically connect right to the control, and the little house that's on the right-hand side will stop blinking. If it's not connected, the little house will blink. So you don't have to connect the outdoor reset, but we want you to because you want that best efficiency. So if you don't connect it, it'll blink. If you connect it, it'll stop blinking. Answer that
Well,
question.
the only exception to that would be as if you enable the Wi-Fi weather.
Right.
Then you
Then
don't
that'll stop.
sensor because the boiler will pick up the outdoor temperature from the internet, the local outdoor temperature. It knows based on where you've installed it, that it should be picking up a local weather station.
Right.
And
Right.
again, this
But
is not part of what we're talking about today, but if you do that
he
as
asked the
well,
question,
even if you have a sensor, even if you use the sensor or you use the internet weather, you can adjust the boiler up to 12 degrees, either higher or lower than what the sensor is reading, to help match it to the system requirements. So there's a lot of fine tuning available there.
right. And then also go back to this kind of jumps in the right. Nathan had a question about, turn downs automatically. Yes, the turn downs automatically set. It's calculated depending on the AHRI standards or AFUE efficiency. But keep in mind, and to go back to Nathan's question here, he says, longer run times. Longer run times are going to be good at lower temperatures because what's going to happen is you're going to allow to reach that dew point of that natural gas and LP, like Ted said, stay on 140 degrees, and you'll be at your peak efficiency. So that is where you're going to get your efficiency. Don't worry about the turn down. The turn down's more concerned about the BTUs that are trapped left in the boiler after you're done. If you look at that, you want to look at constant runtime, good heat distribution, get rid of the heat, constantly running. So to answer your question is longer runtime, and you'll be fine.
Let me just reiterate this. This is turn down is looking to match the boiler output to the load. So
right.
Let's say you've designed a 100,000 BTU system at design temperature. Let's go to Syracuse, for instance, because that's what we were just looking at the chart, right? So in Syracuse, you're designing for 0 degrees. And let's say you have a building that needs 100,000 BTUs at 0 degrees. The fact of the matter is, even in January, the average temperature is 24. So that's only 75%, or actually, no, I'm sorry, that's 66% of your design. So really, that boiler wants to be operating at 65% of its capacity. And so that's what turn down is doing. Turn down isn't changing a temperature, an outlet temperature. It's changing the overall output of the boiler, right? In other words, it's reducing the output, but not, so it's matching the load, but it's not changing the temperature. So turn down is matching the boiler output to the load. Reset is matching the temperature to the load. So
Now,
if you go back to that reset, that cruise control analogy, in other words, as the temperature outside goes up, the system temperature can go down accordingly and still match the load. And in an ideal system, you're utilizing both turn down and reset, which will increase the system life, will prolong the runtime, so you're operating for longer periods of time at steady state, and will make for the best occupant comfort at the same time you're achieving the maximum efficiency.
That was a good question. Good conversation.
And here's a good chart that actually kind of just emphasizes that. So you can take a look at this. See, you see modest increases in efficiency at lower outputs. So the lower output is turned down. So here you've got 100%, 80%, 60%, 40%, and 20%. And you can see modest efficiency increases at lower outputs. But if you look at system temperature, in other words, return water temperature, your efficiency goes way up at regardless of what your output is as you drop your return temperature. So this chart is basically showing you both those things we were just talking about.
I've been saying that for a long time. I like that. That's a good chart. The problem is I have to put my glasses on to see it.
Yeah, I'm sorry, it's a little bit fuzzy, but I think
I've been using my glasses for a lot more things to look at, like my phone menus.
so. You've got 5 different process lines based on your output. So there's your turn down, and then you've got the thermal efficiency as a function of return water temperature, which reflects your reset. So this is showing you both turn down and reset at various outputs.
All right. Looking good, Teddy. Looking good.
All right, and that's what I got.
Thanks for watching the video today. If you'd like to check out more videos, see the link below. Don't forget to like, share, and subscribe to our channel for all the future updates. And also check us out on Facebook, LinkedIn, and Instagram.